Hi dear students, welcome back all of you to the physics online class. We started the chapter dual nature of the radiation and the matter, right? And in the previous video I explained you the point of how the photoelectric effect will takes place, and there in order to understand that photoelectric effect we need the experimental setup, and in that experimental setup we have seen that we have used an evacuated chamber that we are called evacuated test tube, so it is can be taken T, and this is supported with a quartz window that is a W, and there is a monochromatic source, yes, and in the experiment we have used two plates. One is a plate C that is called emitter plate, this is called emitter plate, and the another plate that is a plate A is called as the collector plate, right? And in the previous video you learnt that the effect of intensity of the incident light with respect to the photoelectric current. Yes, what is a photoelectric current? The current produced due to the flow of the photoelectrons when the radiation of suitable frequency incident on the metal surface, it emits the electrons, it removes the electron, that electrons only called as the photoelectrons, and when that photoelectrons are moving, they are flowing, they constitute the photocurrent. Yes, and the previous class I used one term photosensitive material. What are photosensitive materials? The material or the metal which can produce the photoelectrons when it is irradiated with the frequency, that is the light of suitable frequency. Yes, and a few of example I can take the zinc and magnesium. Zinc and magnesium are the two photosensitive material which are sensitive for the ultraviolet radiation. Remember dear students, zinc and magnesium, these two are photosensitive for the ultraviolet radiation. What does it mean? If zinc and magnesium are photosensitive for ultraviolet radiation, means when ultraviolet radiation falls on the surface of zinc or the magnesium, then only the photoelectrons are emitted. Okay, so that is what we call zinc and the magnesium are the photosensitive for the ultraviolet light. Then, so we can use another example for this, that are alkali metals. What are alkali metals? Under this I can use the example of alkali metals, example lithium, sodium, potassium, rubidium, right? So like this etc. many alkali metals are there. These are photosensitive for the visible light. These are photosensitive for visible light. What does it mean? When visible light of suitable frequency falls on the surface of lithium or sodium or the potassium, rubidium, that means alkali metals, they emit the photoelectrons. So they are called photosensitive for the visible light. See, my question, if ultraviolet radiation incident on alkali metals, is it possible to get the photoelectrons? No, very less chance to get, because every metal surface has a particular work function, as I told earlier, yes, and it is having particular frequency of the radiation. When it incident on metal surface, then only the photoelectrons are emitted from their surface. Okay, yes, and previous class we talked about the experimental setup of photoelectric effect, right? The one factor we discussed already, that is first one, effect of effect of intensity of incident light, intensity of incident light, on photoelectric current, photoelectric current. Yes, we discussed that here if the intensity of the incident radiation increases, the number of the photoelectrons emitted from the metal surface also increases. Per unit second, how much the photoelectrons are emitted, accordingly the number of the electrons emitted per second that constitute the photocurrent there. So, we came to know that if the intensity of the light is increased, then the photocurrent also increases. So, by this very clear point we got that if intensity of the light is increased, photoelectric current increases, or the photocurrent is directly proportional to the intensity of the incident radiation. If the intensity variation is taking, if it is decreasing, then photocurrent also decreasing, because the number of the photoelectrons emitted per second also decreases. If intensity increases, similarly the photocurrent also increases. This is a graph which connect between intensity of incident light and the photocurrent here. I hope the point, that is the effect of intensity of incident light on the photocurrent, is clear. Yes, and today we will discuss the next point of that, effect of the second factor the second factor on which the photoelectric current depends, effect of potential difference, between two plates, C and A. As you know, C is the emitter plate, A is the collector plate, right? So, then here first let me explain you when the PD across, when the potential difference across the ends of the collector plate and the anode, that is the emitter plate, is 0, when the potential difference between the collector plate A and emitter plate C is 0, there no more current is produced in the circuit, because PD only not applied there. Yes, so therefore here the current produced is very negligible. Then how that current is produced? Because we know that the radiation of certain frequency incident on the emitter plate here, and as soon as it incident, the photoelectrons are emitted from the surface of the emitter plate, and that are moving towards the collector plate due to the flow of that small number of the photoelectrons that constitute very small amount of the photocurrent in the electric circuit. Okay. So, this is the first condition here, the effect of the potential difference. Am I clear? Then the second condition is, if the emitter plate is connected with the positive terminal of the battery. See here in the diagram you can see properly, this is the emitter plate. This emitter plate we are connecting to the positive terminal of the battery, and the collector plate A is connected to the negative terminal of the battery. As the potential difference across the ends of that battery goes on increases, what the thing is observed here, the photocurrent also increases. Very beautiful phenomena, because here what radiation we used that has in this condition constant frequency. Here we are using constant frequency and intensity. We kept the radiation of constant frequency and constant intensity, but what the quantity we are changing? The potential difference between the two ends of the battery we are changing. Yes. So, the first point noting here is, if the PD across the ends of that conductor, that means a plate, increases, then see here PD is increasing, means this is connected with the what? The emitter plate. Due to the increase in the potential difference, more number of the photoelectrons are emitted here. When the number of the photoelectrons increased are more, due to the positive, see here the emitter plate is in the positive and electrons have the negative, and here this collector plate is in negative. Okay. So, in that condition what happens? There is increase in the one point here. So, here we are keeping first negative potential and here positive. Yes. Okay. So, then what happened here? Due to the increase in the, so number of the electron, they have the negative charge and collector plate has the positive charge. In that condition, it is attracted towards the collector plate. Yes. And as there is increase in the, so that potential of the collector plate, then what happened? The more number of the photo current also increases. That I want to explain with the help of the graph here. This is the photo current what I can use, and here I use the PD of collector plate, that is PD means what? Potential difference of collector plate. And you can see that as the potential increases, the photoelectric current also increases and it reaches one maximum value. Okay. And again, if you change with the radiation with the another intensity, there also you can observe that there is increase in the photo current if you increase the potential of the collector plate here. Okay. So, then as you are observing here, this is indicating that the potential difference of the collector plate is directly proportional to the photo current. As the potential of the collector plate increases, the photo current also increases. But see, at a particular potential, maximum potential of the collector plate, the current of that obtained is maximum. So, that current we name as the saturation current. What it is called? Saturation current. What is the saturation current? The maximum current. Which current it is? Maximum photo current. The maximum photo current obtained when the collector plate is kept at more positive potential. The maximum current obtained when the collector plate is kept at a more positive potential. I hope the definition is clear. See, dear students, in this chapter any point may be asked here for the 1 mark. What is the saturation current, and at the saturation point how will be the potential of collector plate? Like this, a few of the competitive questions also may come. Yes, you have to study each and every point in the concept. Okay. So, I hope this point is clear. Okay. So, then this is the condition, this is the graph, this is showing for what? The positive potential of the collector plate. Then see, first condition is both A and C are at the 0, PD across them was at 0. Then the second case what I talked, A, that means what? Collector plate we kept at the positive potential, and C means what? Emitter plate, it was kept at the negative potential. Yes, and the last condition here to study is if we keep the collector plate in the negative potential and the emitter in the positive. What will be the condition here? See, slightly I can change this condition here like earlier. If I keep here the emitter plate as the positive and the collector plate as the negative here. Yes, what happens if we increase the potential of the collector plate, right? Slowly the amount of the electrons which are emitted from the emitter plate will be reaching to the collector, but immediately the strong repulsion will take place between the collector plate and the electrons. Why it is so? Because we have kept the collector plate at the negative potential, electron also has the negative charge. We know that like charges will repel each other. Okay, so due to that repulsion between the photoelectron and the collector plate, there is a decrease in the photocurrent. Remember this point, there is a decrease in the photocurrent. Therefore, as the negative potential of the collector plate increases, the photocurrent decreases. You can see here the graph, this part of the graph, the photocurrent decreases. Finally, it reaches a zero value here. Okay, and see here, there is a one potential. What potential it is? Negative potential. So this is the left part of the coordination system. We know that here the negative x-axis will be there. So I am using here negative V0. What the V0 is called here? V0 is called stopping potential. Stopping potential. Or it is also called cutoff potential or the stopping potential. Then if question comes, define stopping potential. Define stopping potential. The maximum negative potential of collector plate, the maximum negative potential of collector plate for which the photocurrent is 0, for which photocurrent is 0, that is called as the stopping or the cutoff potential of the given photoelectric effect. Is that clear? See, in this condition, when we are dealing with the effect of potential difference between the plates C and A, by keeping the frequency and intensity of the incident radiation constant, we come to know the two terms. One is a saturation current, another one is a stopping potential. Yes, saturation current means what? The maximum current obtained when the collector plate is kept with a more positive potential. Okay. Then the second one is a stopping potential. The stopping potential is a what? Maximum negative potential of collector plate, maximum negative potential of collector plate for which the photocurrent is 0. And by the graph also you can see the concept very clearly. Yes, and that stopping potential in the formula we are representing with the letter V0. So in the formula, wherever the V0 will come, you have to take and consider that as a stopping or the cutoff potential. Okay. So then in this point, we also conclude two concepts. One is, after the photoelectric effect, all the photoelectrons do not have the same kinetic energy. Remember, dear students, here we know that many number of the photoelectrons are releasing or so they are coming, moving here. But do you think all the electrons are moving with same kinetic energy? No. The point you have to understand is all electrons, that are which electrons? All photoelectrons. Photoelectrons do not move with the same kinetic energy. Do not move with the same kinetic energy. Then, so how to increase that kinetic energy? If you want to increase the kinetic energy, we have to increase the potential difference between the battery plate. Yes, therefore, here I can write the kinetic energy is equal to E into V naught. We can connect the kinetic energy of the photoelectron can be related with the stopping potential by this formula, and here the kinetic energy we can change as kinetic energy is equal to m half mv square maximum. This is equal to E V naught. Remember, here V means what? This is the maximum velocity of the photoelectrons, and here V naught means what? Stopping potential. So this relation also we can bring for the photoelectrons with their kinetic energy and the potential, that is stopping potential. Okay. So this is the point in which effect of potential difference between the two plates of the the collector and the emitter we discussed. Now the next factor need to be discussed is effect of frequency. Effect of frequency. Here we keep the potential difference and intensity of the light constant. Intensity of light remains constant. Okay. Here also we will study one graph. That graph explains us how the frequency is related to the photocurrent and how that is also related to the stopping potential, right. Okay. The next factor where we discuss effect of the frequency by keeping the potential difference and the intensity of the light constant. Yes. So here I want to show the graph. Again, there is a graph of photocurrent versus, okay, here I can use, right. So potential difference of collector plate, right. Here it is observed that it is the nature of the graph I can use here is like this. Yes. So this is the condition of saturation current. And here I can write V naught 1, that is V naught 2, that means second stopping potential, and here V naught 3, that is the third stopping potential. Yes. This graph explains that if the frequency of the incident radiation increases, the kinetic energy of the photoelectrons also increases. Remember, dear students, these are related to each other. If, for example, assume this is a metal surface. First, we incident radiation of a frequency, take 15 or 50 hertz, right. Then during that few number of the electrons are emitted, but their kinetic energy is less, they are moving very slowly. Then if you incident a radiation of the frequency nearly 80 hertz or 100 hertz, immediately we can observe that the kinetic energy of the photoelectrons increases. And see, just now I have given a relation that if the kinetic energy is related, that kinetic energy of photoelectron is increased, then definitely what will increase here? The stopping potential of the, so electron also increases. Because in general also we know that, assume one person is running very fast, isn't it? That running very fast means what? He is having a more kinetic energy. In order to stop that person, in order to make him stop, what you will do? You will apply more stopping potential on him, isn't it? Same thing is observed in the case of photoelectric effect. Yes, where we are observing that if the frequency of the incident radiation increases, accordingly the kinetic energy of the photoelectrons increases. And if the kinetic energy is increasing, by formula and by general concept also, the stopping potential also increases. Therefore, so the graph will tells that if you are using a frequency nu1, then the stopping potential for that electron is, that is V01 is a stopping. And if you are little increased frequency, that the second line shows here, this is having a frequency of a nu2, then its a stopping potential also increases. And here also if you are using a frequency of a radiation, that is the nu3, there also you can see the value of that stopping potential, that also increases. So by this graph, for an increase in the frequency, there is increase in the stopping potential, but the current remains the constant, that is reaching maximum value. It is called the saturation current. Am I clear? So then from this graph, what relation we can give here? We can give that the frequency, first frequency is less than the second one, it is less than the third one. Or this you can also write in this order, nu3 is greater than nu2, nu2 is greater than nu1. And similarly, if the frequency is greater, the stopping potential is also greater. Therefore, related to this, we can also write the stopping potential, that is V03 is greater than minus V02 is greater than minus V01. Okay. So, these are the concept related to the effect of the frequency when by keeping the potential difference and the intensity of the light constant here, and we brought the relation. Yes, and the last effect is effect of nature of material used. Yes, and here also we have a graph where it is plotted kinetic energy versus the frequency, and for this we can see the two different material of the plate, two different material, call it is a material A and this is a material B here. So, when you consider here effect of nature of material we are taking means, we are taking PD is remains constant and the frequency constant, intensity of the light also constant. But what we are changing here? The material of that plate only we are changing. So, by this we can observe that for a metal or for the metal A, the frequency of the incident radiation is taken to be nu1 here. And for the metal B, for that also the frequency of incident radiation changes. Then, so this will shows that whenever the particular frequency will incident on the particular metal, then only it emits the photoelectrons. See, before the nu naught one, there is no increase or decrease in the kinetic energy for the metal A. Yes. So, from origin to particular value of the frequency is reached here for the metal A. When that particular frequency of the radiation will incident on the metal A here, then what we obtained? The kinetic energy means photoelectrons are emitted and they started to run, they started to move. So, only the kinetic energy is increased. And this line shows that kinetic energy and the frequency of photoelectrons are directly proportional to each other. If the frequency of incident radiation increases, kinetic energy of photoelectrons also increases. But every metal has a particular minimum frequency. Remember that minimum frequency only called as the threshold frequency. What it is called? Threshold frequency. Am I clear? And a threshold frequency is represented by a letter called nu naught. What it is? Nu naught. So, these 2 points, these are the what? Up to now what the point we discussed, everything related to the photoelectric effect and the effect of the factors which effect on the photoelectric current. The first factor is intensity of incident radiation. Second factor is the effect of potential difference of the plate A and C, and next one effect of the frequency, and the next one effect of nature of material. And this is very clearly tells that every metal has a particular minimum frequency above which only it can emit the photoelectrons. Then that minimum frequency only we call as the threshold frequency. So, for every metal the minimum threshold frequency is different. Okay. So, this completes the concept of the factors. Remaining part we discuss in the next class. Thank you for watching the video.